Welcome back. Module 5 here. We are talking about location information. We're talking about GPS. We're talking about these fundamentals of how we notate where we are, where things are, how we communicate with satellites and systems to understand our location in real time. All these things kind of bundled together, heading toward Lab 5, where you'll create some data based on some features and ideas on your own. So here's that overview again, some basics on location, some basics on GPS, and again, some questions and answers as you have them. Keep sending them in. I'll keep answering them. And of course, GIS potpourri coming after this. But we're going to start with our understanding of location. And we can represent or describe location functionally in two ways: relative location and absolute location. Relative location requires us to have some understanding of relationship, of distance, of comparison. Relative location is all about comparing thing X to thing Y. Again, it's those basic terminologies that we've learned in primary school or elementary school or kindergarten or wherever. The dog is on top of the desk. The dog is in the house, all those kind of things. The cat is on the table. All of these kind of things are what we need for relative location. It assumes that we understand the two things and we understand the words that are linking what they're up to. Relative location. Absolute location requires some kind of precise understanding of a measurement technique, or requires a precise set of coordinates, or it requires, a rigorous defined definition of something, which we can then use to relate to our coordinate system in general, our measurements in general, so on and so forth. So it's more locked into a grounded universal idea. So relative location positions us in relation to another object, or positions something in relation to something else. Hawaii is south of Alaska. Relative location. How far south? Don't know. What is in Alaska? I don't know. This implies Alaska is north of Hawaii. We don't know anything else about the locations of these objects other than Hawaii is south of Alaska. And that might be enough. Where is the coffee shop? Oh, it's across from the grocery store. Oh, okay, I know where the coffee shop is. Sometimes relative location is more than enough to get us there. Many times it isn't. But to get absolute locations, we need a standardization. We need a system. And we need that system to be rigorously defined. So when we're talking about, say, latitude and longitude, we're not only talking about degrees north, degrees west, but we're also talking about how it is aligned to an underlying datum. Datums are our measurement systems that we've established to all be able to talk the same coordinates, the same grid. We could measure in other units and connect it to datums that measure in feet or meters or have different reference points. All of these things are ways we can function within absolute location. We have some kind of established place or established norm, and then we make our measurements or our coordinates from there. And really, when we're thinking about what GIS is and what GIS can do, we can think about this idea that spatial is special. We've emphasized this throughout the course. GIS is something for organizing and arranging spatial data. With spatial data, you have new capacities and new capabilities than with non-spatial data. Spatial data gives you more power than just a spreadsheet. All of these things have been emphasizing the spatialness. But when we have spatial data, we need to have this system, this underlying linkage between coordinates, between attributes, and that underlying spatiality. Remember, anything can be in a GIS if you have attributes, spatial information, and a way to link them. But if we have spatial information, we have to have spatial information that we can all agree on how to use. GIS only works when we have a rigorous way of defining and understanding what these locations mean. Think back to our digitizers, Roger Tomlinson, and those light boards and the pre-ARC node model days. We couldn't compare those components when they didn't have a unified frame of reference, when they weren't just lines on a digital axis that had no relationship to any other lines on any other digital axis. So building up our absolute location, building up our rigorously defined system, gives us spatial data that can be shared and transformed and understood across systems and across understandings. Now, fortunately, we all do live on the same planet, and our planet is fairly roundish. So having spatial data really allows us, or using our planet for spatial data really allows us that kind of common frame of reference. To make that abstraction, we need to go a little bit more in depth, though, have some kind of measurement than saying, yeah, Earth is round-ish, kind of. Well, what kind of round? What kind of function? And the thing that we have to kind of stop and think about is first, and just really establish and sit down and confirm, is that the Earth is not flat. The Earth is three-dimensional. And if the Earth were flat, everything that comes from coordinate systems and map projections and all the things that we're going to struggle with later on in the course would actually be so much easier. If the Earth was a flat plane, two-dimensional, and only had one shape, and we didn't have to worry about transformations between 3 dimensions and 2 dimensions, our lives would be incredibly easier. Unfortunately, the Earth is three-dimensional, so we got to deal with all of this. Now, the other advantage we have on the Earth is that the Earth's surface is continuous. There are no gaps. We are not two hemispheres just floating out there. We've got a continuous surface. And that continuous surface we generally refer to as a sphere. Spherical Earth. There it is. As we are thinking about our spherical Earth, we generally conceptualize and represent the Earth as a sphere using two directions or two axes of measurement, latitude and longitude. When we think about latitude and longitude, we are thinking about how we've decided to divide the Earth up into functionally spherical coordinates. While the Earth might not be a perfect sphere, it is still roundish, and we can assume it to be a sphere with only minimal problems. So here's our crash course on latitude and longitude. If we're looking at latitude, 0 degrees, that is the midway point between the poles, the North Pole and the South Pole, also referred to as the equator. The equator is at 0 degrees latitude. As you go north, your latitude values are positive. all the way up to 90 degrees north. That's the North Pole. That is the furthest north you can go, and it is the most degrees of latitude you can have. No more than 90 degrees of latitude. Going the other way from the equator, 0 degrees. If you start at the equator and then down south, you would have negative values all the way down to negative 90 degrees latitude. That is the South Pole. There are no further negative latitudes you can have, just negative 90 of them. So our latitudes run from 90 to negative 90. The northern hemisphere is positive. The southern hemisphere is negative. Flip it the other way, and you have longitudes. Longitudes run from 0 degrees, which is by arbitrary definition, the prime meridian, while the equator is the middle of the planet, and there's no other way to bisect the planet into 2 even hemispheres, north and south, other than the equator. Try cutting up an orange sometime. You can't get it evenly unless you chop it on the equator. However, for longitudes, any of these lines could cut the Earth into 2 even halves. But it's for long-standing geopolitical, colonialist reasons that 0 degrees runs through the prime meridian in Greenwich, England. So that's our 0. If you head east of the prime meridian, your longitudinal values go up until you hit the opposite half of the planet at 180 degrees east, positive 180 degrees east. This is referred to as the international date line, though the actual international date line zigs and zags for political boundaries. It's a big problem when your country's in multiple days at the same time. So 0 degrees to 180 degrees. 180 degrees is the most degrees of longitude we can have. There are no more. If you swing back the other way, 0 degrees at the prime meridian, and then you go west, your values decrease. They are negative. And these negative values continue going down until you reach the international date line at negative 180 degrees west longitude. You cannot have fewer longitudes than negative 180. So longitudes run from 180 degrees east to negative 180 degrees west. 0 degrees at the prime meridian. Your eastern hemisphere is positive. Your western hemisphere is negative. None of it is flat. There's our little recap of our spherical Earth. We use spherical coordinates, although the Earth is not a perfect sphere. It's easier that way. And our various translations and work with deeper geodesy, which we'll get to in a few modules, allow us to make that conversion between spherical coordinates to the actual shape of the Earth, as we've defined it at certain times. Our lovely Earth. Not a sphere, but roundish. We'll pretend. If you want to make the quickest map ever, just draw this. That's 0 degrees longitude, that's prime meridian. 0 degrees latitude, that's the equator. One of the really important things to keep in mind, especially as you're gathering data or working with data in different parts of the world, is knowing your signs. Not those signs, and not those signs either, but your latitude and longitude signs. We remember that positive latitude means that you're in the northern hemisphere. Negative latitude means you're in the southern hemisphere. Positive longitude means you're in the eastern hemisphere. And negative longitude means you're in the western hemisphere. So UMass Amherst, where this course is based, where I'm based, positive latitudes, negative longitudes. And you can see for the rest of the world where your positives or negatives might be.